Welcome back to our complex analysis seminar online, complex analysis and allied topics. Yes, and we are very happy to restart with Eva Gallardo Gutierrez from Madrid, who's going to talk about invariant subspaces for positive operators.
All right. Thank you. Thank you so much, Filippo, Nicola, and Marco for organizing the seminar. It's a great pleasure for me to be here, or, or at least to present something online in this seminar. And I'm going to talk about invariant subspaces for positive operators. And when I asked Filippo about the kind of audience I could expect, he was saying this was like a colloquium. So the first part of my talk is going to set up the general framework why studying invariant subspaces. And clearly, this is probably well known for senior people in the audience, for people who work in operator theory, but for me, the invariant subspace problem has been during almost a century one of the most intriguing questions within the field of operator theory. And it asks if there exists a linear bounded operator in a Hilbert space without non-trivial closed invariant subspaces. For a subspace, we will consider closed subspaces, and invariant means that T of n is contained on n, and clearly the trivial ones are 0 and the whole Hilbert space. Posed in this way, clearly there are two remarks that must be considered. The first one is that in the finite dimensional complex Hilbert spaces, the situation is quite easy, and it is a consequence of the Jordan canonical decomposition, the Jordan canonical form, and every linear bounded operator in a finite dimensional complex Hilbert spaces it has a non-trivial closed invariant subspace. And for the case of non-separable Hilbert spaces, the situation is also easy in some sense. It's enough to consider a non-zero vector in the space and then the linear span generated by the orbit of such a vector. That the subspace, if we close it, it's invariant, it's not zero, and it's not a total, it's not the whole Hilbert space because it's the Hilbert space is non-separable in that case, and that one is separable. So basically, the invariant subspace problem is really posed, or it's really opened in the context of separable infinite dimensional complex Hilbert spaces. And oops, this is what it said here. And there is, from my humble point of view, an intrinsic difficulty. And the intrinsic difficulty, and this is the message that I want to basically transfer to you today, is that there are no classes of well-known examples that somehow we can extrapolate to the general theory. All the examples that are known to have invariant subspaces, those invariant subspaces are either easier to construct or they are attached to the nature of the examples. Clearly, it's well known that there are classes of operators with invariant subspaces, with non-invariant subspaces. Probably the larger class in some sense are normal operators, and this is just a consequence of the spectral theorem for normal operators. So normal operator has non-trivial closed invariant subspaces. Compact operators are another large class, and the idea is that the spectrum of the compact operator is well known, is just a sequence of eigenvalue. This can be empty, union 0, and whenever the spectrum is just reduced to 0, that means that the operator was nilpotent. Von Neumann in 1951 proved that every compact operator, every quasi-nilpotent compact operator has a non-trivial closed invariant subspace. For a while, it took Adams and Smith proved the general context in the inseparable Banach spaces. Another class that we can add in this introduction is Lomonosov operator. Clearly, the Lomonosov theorem was a result that surprised people working in operator theory and asserts that if you have a linear bounded operator, which is not a constant identity, of course, and it commutes with a compact operator, it has a non-trivial closed invariant subspace. Indeed, something more is true. It has a non-trivial closed hyper-invariant subspace. That means that it is an invariant subspace for every operator in the commutant of T. But not every operator satisfies Lomonosov hypothesis. That took a while to be proved, and it was a result proved by Hadwin, Norgren, Rajavi, and Rosenthal in 1980. They proved the existence of a weighted sheaf acting in L2 such that if a compact operator which commutes with a non-zero non-scalar operator in the commutant of such a quasi-analytic sheaf, then such a compact operator is the zero operator. And this result will be important in what I will describe later, so just keep it in mind. I mean, this operator has lots of invariant subspaces. It's a weighted sheaf in L2, but it does not satisfy Lomonosov theory hypothesis in some sense. Clearly, the situation in the Banach space setting is well known to be different, and in that sense, probably the most striking statement was due by Enflo in the seminar Maurice Bars in the École Polytechnique in Paris, and he asserted that there exists a separable Banach space, infinite dimensional, such that and an operator acting on that space such that T has no non-trivial closed invariant subspaces. The result took more than 10 years in order to be referred and finally published. And in the meanwhile, Charles Reid was able to construct invariant subspaces for, was able to construct operators without non-trivial closed invariant subspaces in a very, let's say, classical Banach space, which is little L1. Actually, one of the most striking results in that sense provided by Charles Reid is that the operator that he constructed, though it has not non-trivial closed invariant subspaces, power of it, any power of it has. That was something that was quite remarkable, at least from our perspective. And in a joint work with Charles Reid, we were able to construct a bounded linear operator T acting on little L1 such that not only T, but no polynomial in T has non-trivial closed invariant subspaces. Indeed, such an operator can be constructed in order to be quasi-nilpotent. As I said, the spectrum is going to be reduced just to zero, and any function in T, any analytic function in T is therefore well-defined and as a functional calculus, and it has no non-trivial closed invariant subspace. But once again, all these techniques were really attached to the nature of the operator. And indeed, in that sense, there have been quite remarkable results provided by Sophie Gribaud and Maria Roginskaya, trying to see if those operators are able to be constructed, or at least to shed some light in the context of Hilbert spaces, infinite dimensional separable Hilbert spaces. All right. Which is the setting of this talk? It's going to be an infinite dimensional separable. I do like usually complex, but it can work also on real Banach spaces. And we will consider that our Banach space has a Schroeder basis, or just simple a basis. That means that for every vector in the space, there exists a unique sequence of scalars such that we can represent the vector. It's well known for people who work in Banach space theory that there are separable Banach spaces without a basis, and that construction was due to M-flow. All right, if we have a basis, then we have a natural closed cone associated to the basis, which is defined this way, that's with coefficients, positive coefficients, and it's clearly a cone because it satisfies the three conditions that a cone should satisfy. And having a basis and a cone, we have a partial order automatically determined. Two elements of the space y is less than or equal than x if and only if x minus y belongs to the cone. And therefore, the pair, the Banach space with the cone, is an ordered Banach space. So we have the basis induce an order in the space. And clearly, the order is expected to play an important role when we ask about operators which are acting on the Banach space. Indeed, a natural definition is that an operator is positive with respect to the basis if it takes the cone into itself, or equivalently, if it takes the positive elements into positive elements. Tx is positive, bigger or equal than 0, for each x bigger or equal than 0. When we have a basis, this is, and we can express the operator as a matrix, which is what it's usual in linear algebra. This linear operator is positive if and only if every entry of the matrix is an element, a positive element for every pair. And if the basis is indeed unconditional, that means that the representation of any vector as a series converge unconditionally, then every linear positive operator is automatically continuous. So it's really strong in that sense, okay? If we want to focus on Hilbert spaces, the basis is separable infinite dimensional Hilbert spaces, little L2, then the basis is unconditional. Anyway, we're going to focus on positive operator with respect to the basis. And surprisingly, there is an open problem that I call here invariant subspace problem for positive operator, open version 2.1, like when you are updating your system in the computers. And if you have a Banach space with an unconditional basis, it's still unknown whether every positive operator, and therefore continuous positive operator, has a non-trivial closed invariant subspace. So in other words, if we have a Banach space with an unconditional basis, little L2, if we like the Hilbert space setting, like I'm Hilbertian, and a matrix that represents my operator with positive entries, it's not known if that operator has or not a non-trivial closed invariant subspace. This is, from my perspective, a bit disgusting somehow, because everything is positive. That should tell us something about the operator. But the situation is probably a little bit worse in some sense. Let us think about our favorite Banach spaces, little LP, okay? And we can even P strictly bigger than 1, okay? Here the result works also for P equal 1. Abramovich, Oliprantes, and Burkenshaw in 1993 proved the following result. Assume we have a positive operator on little LP, a matrix with positive entries, okay? And assume that there exists a positive operator S in the commutant of T, which is locally quasi-nilpotent. That means a non-zero, it's locally quasi-nilpotent, sorry, at a non-zero positive vector. That means that there exists a positive vectors in the sense that I told you before, such that this limit is 0. if the operator is quasi-nilpotent, it is quasi-nilpotent at any vector. So that's always satisfied, for instance, for quasi-nilpotent operators in particular. Anyway, then T has a non-trivial closed invariant subspace. Actually, it has a non-trivial closed invariant idea. I will focus on this a little bit later, but this result was extended after being proved to other classes. Was extended to other classes of Banach spaces, in particular to Banach lattices and to Banach spaces with bases which are not necessarily unconditional. But if you focus on the proof and you read the proof of Abramovich, Aliprantis, and Burkenshaw, there are two main ingredients. The first one is the positiveness. Clearly, that's where our game is happening now. But the second one is the local quasi-nilpotency, and it is not possible going through their proof to get rid of this condition. So we can even ask an open version 2.2 of the previous open problem that I will pose you. Imagine you have a positive operator acting on little LP. Does T have a non-trivial closed invariant subspace? By the way, I can add a few things regarding this question. For instance, if you consider the read operator I told you before, and what it is called the modulus of the read operator, that means just considering the entries of the matrices with a modulus, that would be a positive operator in the sense of Banach spaces. Such an operator has non-trivial closed invariant subspaces, surprisingly. That was proved by Trotsky. So there is still a possibility that this open problem says that it's true. The positiveness gives us that it has non-trivial closed invariant subspaces. In any case, this is opened, and that was the main goal or the main question we were trying to understand in this context. All right, so we have Abramovich, Alipranti, Burkenshaw inside, and the first question we ask is, okay, how is this quasi-nilpotency affecting the whole proof in some sense? Can we get rid of such a condition? And in a joint work with a PhD student, Javier González Doña and Pedro Tradacete from Madrid, the first thing that we did is not complicated, and I will show you a little bit about this, is that there exists a positive operator on a Banach space with an unconditional basis, such that the only compact operator commuting with every non-scalar operator in the commutant is just the zero operator, so it does not satisfy Lomonosov hypothesis, but it has non-trivial closed invariant subspaces. Indeed, it has a lot of invariant subspaces, even non-trivial closed invariant ideals, and it's not quasi-nilpotent at any non-zero vector of X. And clearly, we had some sort of candidate to test the first part of this proposition, and that was the operator constructed by Hadwin, Nogren, Rajavi, and Rosenthal. And this is a complex analysis seminar. And this is the only way I will tell you about complex analysis. How was this example provided? So what they did, what Hadwin, Nogren, Rajavi, and Rosenthal did, was considering the standard weighted Hardy spaces that many of you knows about their existence. You have a sequence of positive numbers, and consider the holomorphic functions in the unit list, such that the norm is given by this expression, and just the chief operator. And the chief operator is a bounded linear transformation if we impose certain conditions on beta n, that in our case is going to be completely satisfied. I will tell you which sequence we will choose, but it's also very well known that that weighted shift on L2 are unitarily equivalent to the multiplication operator on this weighted Hardy, acting on this weighted Hardy spaces H2 beta. That's due to Chills. So what Hadwin, Norgren, Rajavi, and Rosenthal did was, in particular for this weight, they do have a little, a larger class, of course. With this one, it's enough. Take the exponential of square root of m, then the shift operator acting on H2 beta. It's an operator that do not satisfy Lomonosov hypothesis. In other words, every compact operator in the commutant of n set is just the zero operator. Okay, so this example somehow fits in the first half of the result that it's stated jointly with González, Doña, and Pedro Tradacete. So if we consider the unitary equivalent version of this shift operator, what we have is the weighted shift acting on L2 associated to this sequence of weight. As I said, this is not difficult at all. And the second half part that fails to be quasi-nilpotent at any non-zero operator, at any non-zero vector, it's a consequence of a lemma. This operator is not only non-quasi-nilpotent, it's not quasi-nilpotent at any non-zero vector of L2, and even more, every operator in the commutant is also not quasi-nilpotent at any non-zero vector in L2. And the way to prove this lemma is based on complex analysis, the only proof in the whole paper that uses analytic functions, and it used local spectral theory. I'm not going to go into details, but that's the only, we had the candidate, and with that candidate, we tested if that could be an example that somehow strengthened the result proved by Abramovich, Aliprantis, and Burkinshaw. So this is the key example, and why this example has so many invariant subspaces being not quasi-nilpotent and still being positive. And as I said, it acts on a little L2. And the situation comes from analyzing it from the Banach lattice perspective and knowing what it is a lattice homomorphism. Let me give you just a bit of the Banach lattice framework. I'm not an expert on this, but this is not, the notation is more or less a standard. As I said, we have an infinite dimensional separable Banach space with a conditional basis in X, and the order induced by such a basis. As I said before, we can consider the supremum and the infimum of two elements, and this is a standard, okay, notation, and the positive part, the negative part, and its absolute value. The positive part is just the supremum of X and the zero element of the Banach space, the negative part as usual definition. An ideal, as I said before, in a vector lattice is just a subspace, but in addition, it satisfies that if the modulus of X is less or equal than modulus of Y, and Y is in the ideal, then X has to be in the ideal. And whenever we have a norm in a vector lattice, we will say that that lattice is a lattice norm if it satisfies that the norm of X is less or equal than the norm of Y whenever the order is preserved. okay? Then or absolute value of x is less than or equal than the absolute value of y. Accordingly, a Banach lattice, for those who knows about this, is a complete vector lattice, just a cube with a lattice now. And this can be done in a Banach space with an unconditional basis, clearly. And this establishes the following definition in some sense. A linear bounded operator on a vector lattice is a lattice homomorphism if the image of the supremum of two elements is the supremum of the images for every x and y in E. You can give equivalently many conditions that the image of the positive part of an element is the positive part of the image of such an element for a vector, for every element in E, that the image of the infimum of two elements is the infimum of the images of those two elements, and so on. Clearly, if we have an injective lattice homomorphism which is onto, then it's a lattice isomorphism. It preserves the lattice structure and it's bijective. Okay. And what is easy to check is that every lattice homomorphism is a positive operator. So with the key example in mind, what we had indeed was a lattice homomorphism. And what is possible to be proved is the following. If you have a Banach space with an unconditional basis, and you have a lattice homomorphism on X, then it has a non-trivial closed invariant subspace. Actually, it has a non-trivial closed invariant ideal. And that was a first step in order to approach to this open problem version 2.2 in order to understand when positive operators in little LP or Banach spaces with unconditional basis have non-trivial closed invariant subspaces. Let me give you a little bit of what is behind the whole proof. Okay, the first step is trying to identify lattice homomorphisms. And at least we were not aware of this. I will introduce a definition. A linear bounded operator on a Banach space with an unconditional basis is called a weighted permutation operator if there exists a permutation of the natural positive integers and a sequence of positive numbers such that T takes the vector basis En in omega n E associated to the permutation. So this is what we define as a weighted permutation operator. And what we proved is that every injective dense range lattice homomorphism it's a weighted permutation operator. First, you prove it for isomorphisms, and then you extended it to just injective dense range lattice homomorphism. Once you have an identification of the lattice homomorphism with this context, or in this way, the second step that we did was representing them as a matrix, trying to see how the matrix of the lattice homomorphisms are behaving. If we have a Banach space with an unconditional basis, that's our setting, and a positive operator, and the matrix represented, okay, all the elements are positive, bigger or equal than 0, we can prove that T is a lattice homomorphism if and only if each row of A has at most one non-zero entry. And if it is an injective lattice homomorphism, this is happening if and only if A has no null column. Actually, with this, in order to prove this proposition, clearly the order and the fact that the positive elements are mapped, I mean, the image of a positive part is the positive part of the image, plays a significant role in the whole proof. And probably one of the straightforward application of this proposition is that the key example that I showed you before, the example that was provided by Hadwin, Nordgren, Rajavi, and Rosenthal, is a lattice homomorphism because it fits in this context. I mean, the matrix fits in this context. What is not so clear, or at least we don't know how to prove it, is that such matrix, with this matrix representation, the operator is not quasi-nilpotent at any non-zero vector of L2. And there is where we use, or we make use of complex analysis and this local spectral theory stuff. So somehow, as I like to think, complex analysis or function theory is helping us in many senses. The final step in order to prove the theorem I posed is to make partitions of the positive integers in order to provide, and we provide those, the non-trivial closed invariant ideals, and therefore the non-trivial closed invariant subspaces. All right, this is the theorem. As I said, it's probably half a step or a tiny step to the big goal that we were trying, but there is a corollary in that sense, and clearly every lattice homomorphism on LP has a non-trivial closed invariant subspace, which in turn, it's an ideal. So it's more than we expected. And in that sense, the result is sharp because there exist positive operators on little LP lacking non-trivial closed invariant sublattices, in other words, lacking non-trivial closed invariant ideals. This example was provided by Kittover and Wistek in 2007, and it's quite surprising. It's not complicated. We can even give it in, it's a little LP, and then the example is the one that takes the coefficients, the sequence, in the if n is strictly bigger than 1, xx minus 1 plus xn plus 1, and x2 if n is equal to 1. So the matrix of this operator is a two-diagonal matrix where each row is set, the first one has exactly 2 non-zero entries. This operator do not have a closed invariant ideal. And if we compare with the proof, of course, with the ideas of the proof that I told you, the proof seems to work because we have at most 1 non-zero entry in each row. So that's the key of the whole structure, at least of the whole proof that we were able to provide. All right, at this point, I would like to make 2 remarks. One, regarding this last example concerning tridiagonal operators. Actually, Figuribon in 2002 proved the following result. If you have a Banach space with an unconditional basis, as we're having, and a positive operator, which is with matrix representation is a tridiagonal matrix, then it has a non-trivial closed invariant subspace. The techniques are completely different from ours. And this tridiagonal matrix, it's amazing because she opened the question, or she provided, it's an open question, better said. What happens for pentadiagonal matrices, heptadiagonal, I think it's hepta, okay, matrices and so on. It's not known, even being positive, okay? When you see Sophie's theorem, there is a naive question that you can ask. Okay, can these invariant subspaces be chosen to be ideals? As it was the conclusion in the theorem. If you dig a little bit in the area, Rajavi and Trotsky basically told us, no, that's not possible. You can consider linear bounded operator with this infinite matrix, where the stars here, this is a tridiagonal matrix, are positive real number, and it has no non-trivial closed invariant ideas. The main diagonal here is just 0 always. But still, this is quite, I was going to say, quite specific, because what's going on is that if you want to have non-trivial closed invariant ideal, then at least one of the elements in the subdiagonal or the superdiagonal has to be 0. Or in other words, how it is stated, the positive operator T has no non-trivial closed invariant ideas if and only if both the subdiagonal and the superdiagonal of A of the matrix has no null element. So in that sense, this strengthens Sophie theorem. This is the first remark on tridiagonals operators. The second remark that I've been basically making a lot of somehow focus attention, right? Or during all my talk is the hypothesis on the Banach space and the order that it inherits from the unconditional basis. And this is really, really essential in the whole proof. Actually, all I knew about Banach lattices, or my favorite Banach lattices in some sense, are big LP. And they are standard Banach lattices. And here, Kitover and Wistek provided a result that says that there exists lattice homomorphisms without non-trivial closed invariant sublattices and therefore ideals. What happens? The problem here is that the basis is not establishing the order, the standard Banach lattice order in that sense. Actually, among the results that Kitover and Wistek provided among the operators were certain bishop operators. And those bishop operators are known to have non-trivial closed invariant subspaces, and indeed ideal. Just to let you know about these bishop operators, they are associated to an irrational number. We fix alpha, an irrational number. And then the bishop operator T alpha is nothing else that taking a function we compose with a fractional part of alpha plus t and then multiply by t. These bishop operators are what usually we call weighted translation operator or weighted composition operator, where we're composing with this fractional part. And surprisingly, it's the composition of two simple operators. The first one is just a multiplication operator, which multiplying by the independent variable on LP. And clearly, the multiplication operators have lots of non-trivial closed invariant subspaces, as I mentioned to you at the beginning. On the other hand, you had composition operator here also. But it's a composition operator very special. It's just composing with a fractional part, as I said. This is the symbol phi alpha. And this composition operator has a complete set of eigenvectors in this setting. And all of them has associated eigenvalue of multiplicity 1. So a lot of invariant subspaces also. The problem is that when you try to analyze these operators and take a function u, like this one, which is continuous function in 0, 1, a first step, a first image provided a discontinuity at 1 minus alpha, and it flat the graph. A second image of it provided 2 discontinuity now, and it flat a little bit more, and so on and so forth. And these operators are really, in some sense, at least from my perspective, difficult to understand. And they're important because they were posed by Bishop in the 50s as possible candidates for operators without non-trivial closed invariant subspaces in LP. Actually, as possible counterexamples to the invariant subspace problem. Devi proved that if alpha is a non-Liouville irrational number, then the corresponding Bishop operator T alpha has a non-trivial closed invariant subspace in LP. Indeed, it has a non-trivial closed hyperinvariant subspace. And here it's not using Lomonosov theorem at all. Just recall that what a Liouville number is. A Liouville number is an irrational that can be approximated by rationals very rapidly in the following sense. For every n, it's possible to find out a reducible rational number, Pn over Qn, such that we are approximating alpha with this irreducible to order 1 over Qn to power n. So, as I said before, what Kittover and Wistek provided was a second category set, lambda, consisting of non-Liouville irrational numbers, such that for every alpha in such a set, the operator has not non-trivial closed invariant ideals, but they do have invariant subspaces because of Devi result. Clearly, those are homomorphisms, lattice homomorphism, but not with a basis, with an unconditional basis in LP. Oops, sorry. And this established that the hypothesis that we were posing on the space regarding the order inherited by the unconditional basis is essential, in order at least to get ideas, of course. All right. Regarding Bishop operator, it is still an open problem, proving the existence of non-trivial closed invariant subspaces for T alpha for any irrational alpha. There have been extension of Davis result that include Liouville numbers. Actually, McDonald's in the 90s we're trying to focus extending those results to not only Bishop operators, but also Bishop type operator, where the weight is a little bit different. Flatot actually provided a good set, let's say, or a bigger set of Liouville numbers, such that T alpha has non-trivial closed invariant subspaces. And more recently, in a joint work with Fernando Chamizo, Miguel Monsalve, and Adrián Ubis, all of them from Madrid, and we were able to enlarge the set of Liouville numbers such that T alpha has non-trivial closed invariant subspaces. The techniques were completely different to those that we have discussed previously here. They are based on Berlin algebras and a refinement of the approximation of the sequences of the convergence of the Liouville of the irrational alpha. And clearly it's quite attached to the specific behavior of each of T alpha. So I guess I'm not going to go into details in that direction. That's probably for another seminar. But I would like to finish up with a slide that I posed you almost at the beginning. Clearly, in order to understand the invariant subspace problem, or at least in order to shed some light on this problem, and as I said, from my humble opinion, we are not dealing with a well-known class of operator that can help us to understand these general questions. Somehow, all the techniques that we are able to manage to produce invariant subspaces are too attached to the operators in questions. So this is basically the end of my talk. Thank you for your attention. I think I have some references. Let me comment on them. The results by Abramovich, Aliprantis, and Burkinshaw that I mentioned are these two papers. Basically, this is the joint work with Chamizo, Miguel, and Ubis. The results that I were explaining jointly with González Doña and Tradacete are on arXiv, so you can download if you're interested. And our key example that was basic in order to understand what was happening to the lattice homomorphisms is this work by Hadwin, Norgren, Rajavi, and Rosenthal. All right, this is basically all I wanted to say. Thank you very much for your attention.
Thank you very much, Eva. So I think, yeah, we can unmute and clap somehow. Okay.
Thank you.
Are there questions?
I didn't go too fast.
I think it was very well calibrated. Thank you very much.
Somehow just see your slides and, but anyway, I hope more or less you follow.
We can see again now on YouTube.
Exactly.
So are there questions? Nicola?
No.
Otherwise, I have a question, if I can. Or Nicola, did you want to say something, or?
No.
Ah, was just okay. So my question is, do you know if you consider composition operator or even composition operator coming from continuous holomorphic semigroup of the unit disk? Do you have some better result or more specific result out of them acting on some HP spaces, for instance?
In order to understand invariant subspaces, you mean?
Yes.
Okay, if you consider composition operator, probably you know this, induced by a hyperbolic disk automorphism. For instance, take your favorite one, the one that fixed 1 and -1. Okay, on it has two boundary fixed point. Then CFI is not what it is called universal, but it can model any linear bounded operator in a Hilbert space through its invariant subspaces. If you give me any linear bounded operator in a Hilbert space, I can give you, I can tell you that there exists, better said, a non-trivial closed invariant subspace for such an operator, CFI, for the composition operator, such that the restriction to that it's equivalent to the operator that you gave me. As I said, it's not universal, but it satisfies this universal condition because when you consider CFI minus lambda times the identity, and lambda is in the interior of the spectrum, then that it's a universal operator in the sense of rota. But you can't forget about the lambda times the identity because it's not providing any extra information for the subspaces. So you just consider CFI. Clearly, this CFI, I think they can be embedded in a semigroup you are the expert in that sense. What is not so clear is how the semigroup is acting on the invariant subspaces that are modeling any other operator. In a joint work with Carl Cohen, we were trying several ideas by means of the semigroup. But to tell you the truth, we didn't really succeed in giving you something quite interesting. But it would be very nice if the semigroup could tell you something about the subspace that it's modeling. For instance, if I give you the chief operator, which subspace are you giving me? If the semigroup could tell me something about that subspace, because this is an existent theorem. I mean, there is a construction, but it's not possible to identify the subspace. But if the semigroup could tell us something, that would be wonderful. I don't know. I mean, I should expect, that was what we were expecting, but we were not able to make it work. I don't know. But you are the expert in semigroups, and maybe
yeah, but I know very little about invariant subspaces. So.
The situation with invariant subspaces is that it can be, it's very natural if you think about them in finite dimensional, but you can lose almost everything about them. For instance, if you consider rank 1 perturbation of a diagonal operator, consider just a diagonal operator. The matrix is quite easy, just a diagonal, non-zero elements, okay? Has a lot of eigenvectors, a lot of spaces, invariant subspaces. Just consider one rank perturbation of it. It's not known if it, for any rank 1 perturbation, these operators have non-trivial cross invariant subspaces. This is amazing. I mean, from my perspective, at least the message to take home today is that, okay, it's impossible. We cannot say we're trying to understand a little bit better this big question if we're not even understanding easy examples, right? That's what that was basically the message. But anyway, this is it would be nice if the semigroup says something else. Okay.
Thank you. Other questions?
Hi, I don't know if you can hear me.
Yes.
Okay. First of all, I would like to thank because it was a really nice talk.
Oh, thank you.
But if I heard well, in the results of 3 diagonal matrices, there is no so much result for pentadiagonal operators or further.
all the entries positive. You take a pentadiagonal operator in little LP. Okay.
Yes, and my question was if there is something that it lacks, what is the we think change in that new framework?
I don't know if I understand the question. Could you rephrase it or pose it? The problem with the three diagonal, I mean, the idea of Sophie was completely different. She took the three diagonal operator and she studied how those super diagonal and subdiagonal interact in order to produce the invariant subspaces. Okay, this is in this paper. Let me share it. Okay. Do you see my screen now?
Yes.
Okay. This is in this paper, Invariant Subspaces for Three Diagonal Operators, Bulletin of Science Mathematics or whatever, I don't know, the French. Anyway, so what she did was considering the super diagonal and the subdiagonal and establishing the, with a result of Atzmon and Godefroy, if I remember correctly, she was able to provide the invariant subspaces. The basic problem there, and you're assuming that the entries are positive. So you have a lot of tools in some sense. The basic problem is that her result cannot be extended, or at least she was not able to make it work. And I haven't, okay, we were not able also, at least with the techniques we were working with, to pentadiagonal matrices. So just take a pentadiagonal matrix with positive entries. Does this operator have a non-trivial closed invariant subspace in little LP? That sounds like a basic question. As I said before, come on, if we cannot understand easy examples, it sounds like a big mountain to understand a big problem, right? But anyway, and on the other hand, the read operator, I was working very hard with the read operator. The problem with the read operator is that when you express it as an infinite matrix, there is one entry which is negative. And that spoils everything. Indeed, as I said, Trotsky, when you consider the modulus of the read operator, which is nothing else than putting all the entries positive, it has non-trivial closed invariant subspaces. Amazing.
Okay, thanks.
Thank you. Other questions? Comments? Okay, so if not, I think we can thank Eva again for this wonderful talk.
Oh,
thank you very much.
To you.
Muchas gracias.
Thank you, Eva.
It was a real pleasure. Thanks a lot. I hope more or less everything was, you were able to follow with the slides. As I said, it's always easier to be in person, but I hope it worked.
I'm sure.